All right, today we are pulling back the curtain on artificial intelligence. And what if I told you that one of the simplest tools in all of statistics is actually the secret ingredient behind the most complex AI systems on the planet? Let's dive in.
So let's kick things off with the one big question that really frames our whole conversation today. Is AI some kind of totally new, alien form of math? Or is it actually something we've had for a long, long time, just used in a completely revolutionary way? The answer is pretty surprising.
To get to that answer, we've got to start with the absolute most fundamental building block. It's a tool you've probably heard of before called linear regression. But here's the secret. This simple little tool has a kind of split personality, a fascinating dual identity.
You see, you can think about linear regression in two totally different ways. On one hand, you've got the traditional, old-school statistical approach. That's where we, the humans, come in, with our own strict rules and assumptions, and tell the model how it should think. But then, there's the machine learning approach. And this is a total game changer. Here, we make zero assumptions. We just hand the model a mountain of data and say, you figure it out. You find the patterns.
And that right there, that's really the core philosophy that powers all of this. We're not pushing our own biases onto the problem. We're actually stepping back and empowering the machine to find the truth hidden in the data, whatever that truth might be. This is the first absolutely critical step on this journey.
Okay, so we've got our basic building block, this little assumption-free, data-hungry model. But, you can't build a skyscraper with a single brick. The next step is all about scale. And I'm talking about truly mind-boggling scale. In the AI world, we give this little building block a fancy name, a neuron. Now, don't let the biological name throw you off. A neuron is just our good old linear regression model in disguise. Its entire job all day long is to be a tiny calculator. It looks at all the information coming in and just figures out how important or how weighted each piece of info is for making a good prediction. And when I talk about scale, I really mean it. A modern neural network isn't just a few of these neurons. It's a massive, sprawling network of over 1 million of them, all connected, all working in parallel. Imagine that. 1 million tiny calculators, all learning from the data at the exact same time. But this incredible idea creates a huge mathematical problem. So this is the point in the story where our brilliant plan just hits a brick wall, or maybe more accurately, a very, very flat wall. We've got this amazing idea to stack millions of calculators together to create something super intelligent. But there's a catch, and it's hidden deep inside the math.
I mean, the next step seems so obvious, right? You just take one of your linear models, you stack another one on top to make it a bit smarter, and then you just keep going. You add hundreds, maybe thousands of these layers to create a so-called deep network.
But here is the brutal mathematical punchline. When you stack a straight line on top of another straight line, and another, you don't get some beautiful complex curve. You just get another straight line. The entire magnificent structure just collapses back into something no smarter than that single little block we started with.
Yeah, this problem has a name. It's called linear collapse. It's just a fundamental rule of math that says no matter how many linear layers you stack up, at the end of the day, it all just boils down to one simple single linear equation. So our grand plan for deep, intelligent network is at this point a complete and total failure.
But of course, the story doesn't end there. You knew it wouldn't. Because for every big problem, there's usually an elegant solution. And the solution to linear collapse is probably the single most important concept that makes modern AI possible. It's all about one simple idea: learning how to bend the math. And this is the hero of our story, the activation function. Think of it like a little filter or a gatekeeper. After each neuron does its simple straight-line calculation, the answer has to pass through this filter. And the filter's only job is to introduce a tiny bend or a kink into the result. It's a small, non-linear twist that changes absolutely everything. And the transformation is just profound. Before you add this activation function, the network is stuck. It can only think in straight lines. But the moment you add that little nonlinear bend after every single neuron, the network suddenly comes to life. It can learn curves, it can learn all the wiggles, it can finally start to understand the incredible complexity of real-world data, like images and text and sound. Okay, so all this math is fascinating, for sure. But what's the real-world payoff? Why should you care about bending a line inside of a computer? Well, let's look at a really concrete business case. So think about a bank trying to decide who gets a loan. A traditional linear model is rigid. It learns a simple rule, like if your debt is high, your risk is high. It's a straight line.
But a neural network, with this new ability to bend and curve, can discover nuance. It might find something really specific, like, hey, high debt is actually low risk, but only for people in this specific age group who also have this specific spending habit. It finds the exceptions that a simple straight line could never, ever see.
And that's really the crucial takeaway here. The real world is just messy and complex. It's filled with these it depends scenarios. By teaching a machine how to bend the math, we've given it the ability to navigate all that complexity. It can move past simple rules and find the subtle, hidden patterns that actually drive business and science and so much more.
So let's bring it all home. Let's recap this pretty incredible journey we've just been on and see exactly how a simple straight line really does evolve into what we call artificial intelligence.
When you boil it all down, it's really just 3 simple steps. First, we start with the line. That's our machine learning regression letting the data speak for itself. Second, we stack millions of those lines together in the form of neurons. And third, and this is the most important part, we bend the output of every single neuron using those activation functions. That stops the collapse and unlocks the ability to find nuance. Line, stack, bend. That's the recipe. And here are those key terms just one more time. ML, linear regression, was our starting point. The neuron was our building block. Linear collapse was the big villain we had to overcome, and the activation function was the hero that made it all possible. If you can remember these 4 concepts, you truly understand the fundamental architecture of modern AI.
So we'll leave you with this one final thought to chew on. We've just seen how one of the most basic tools in all of math, when you scale it up and give it one clever little twist, becomes the foundation for AI. It really makes you wonder, doesn't it? What other simple, everyday ideas are just sitting around, waiting for their own breakthrough moment to completely change the world?